Okay. Over the years, over the millennia, the whole model of the atomic structure has been evolving. It started off with very simple 4 elements. Has evolved into something called a quantum mechanical model now, which is a very interesting model. Quantum mechanical model basically has all the horrendous math associated with it. I mean, it's really ugly math, triple integrals and wave functions and all this stuff. Well, basically what it gets down to is electrons do not go around the nucleus in a planetary orbit. There's a lot of reasons why that model doesn't work. And that's called the Bohr model. You get a Nobel Prize for this. But since then, there's been a lot of, now I'm talking about 120 years ago. I'm not talking about last year, I'm about 120-ish years ago, quite a long time ago. People like Einstein, de Broglie, including Bohr, a number of physicists at the time came up with this model. And it's totally statistical. And what it says is there's a probability of finding an electron somewhere around the nucleus. And then they give the probabilities, high to low. For example, if we went over to Rayleigh's and we went around Rayleigh's building, we would find one spot near a door where there's a whole bunch of cigarette butts. No other area's got cigarette butts, but it's one area. So statistically, if the odds of finding a cigarette butt are higher there than any place else. But we don't know how the cigarette butts got there. They could be an employee, a customer, a bum. We don't really know, but there's a whole bunch of cigarette butts there. And that's basically what the quantum mechanical model says. It says this area, you'll find an electron, probably, but not this area. Just like out here. What are the odds of finding a cigarette butt out there? Low or high?
Low.
Really low, right? But not 0, though. It's probability. Okay, so now we're going to talk about what those electrons are doing around the nucleus. Okay. In physiology, sodium and potassium are critical for neurons to work. And your body has to distinguish between potassium ions and sodium ions. This is why potassium is important in your diet, by the way. And so is sodium. It's easy to get a ton of sodium. It's harder to get potassium. But this is why. And the difference between these two is on the periodic table, you have sodium and potassium. And sodium is smaller than potassium. And your ion channel can distinguish the size. And that's what allows one to go through and one to not, or to be distinguishable between the two. Okay, so we're going to talk about a lot of these trends and why they exist. There's things like ionization energy, electronegativity, size, a whole bunch of stuff. As you know, the periodic table was designed from the ground up for its periodicity, for its periodic nature of chemical characteristics. And then Mendeleev was the second person to do this. The first one before him was a geologist. And he arranged the periodic table, as you know, in columns of similar characteristics. Now we're going to delve into that, why that is so today. We're going to look at things like, what does potassium and sodium have in common? They're in a group together. What is their electronic configuration similarities? His periodic table was very simple compared to the one we have now. There were a bunch of holes in it, but based on the periodicity of his table he invented, he was able to actually predict what those undiscovered elements characteristics were. And it proved to be right. So it was a very powerful device he invented. Okay. So it allows us, the periodic table, to predict the element's chemical characteristics. Is it going to form an ion easily? Is it not going to form an ion easily? If it forms an ion, what is its charge? Things like that we can predict if we know electronic configuration of the element of the electrons that make up that element. Okay. So we're going to do something called electron configurations. We spent a fair amount of time doing this. And what that does, it says a bunch of information. These are organizational levels. And there's one more piece to this that's not going to cover in a minute. These are the organizational levels at which this electron has been assigned. First one is the most fundamental. It's called the principal quantum number. The second one is called a sub-level. And this one says how many electrons are in that sub-level. And then we're going to actually say each electron spins, and when it spins, it creates a little magnetic field, just like the Earth does. And it's either going one way or the other. So we have spin, we have the number of electrons in the orbital. Now, this orbital is not the same as orbital as in Bohr's planetary model. Yeah.
Yeah, so while I was reading the chapter, I was just wondering the space between the nucleus and the electrons, there's nothing.
Correct. Nothing.
Nothing.
Okay. Bohr came up with that. Bohr said electrons on his orbits only are allowed to stay in the orbits. They're not allowed to wander off. Same with the quantum mechanical model. Quantum mechanical model just refines Bohr's model. But yeah,
It never changes.
it can change if you lose or gain electrons. It'll change its character.
But so it's like relative to like a unit circle almost, right? So it'll stay with that outside boundary.
Yeah, but it could change in size too. Not in shape. Well, it could change in shape as well. Depends on, yeah, if you fill up the orbital or take electrons away, so the orbital doesn't exist anymore. So it's just hold that thought. Okay, so we have 4 items to contend with. One is and that'll be from 1 to 7. Okay. Notice this goes down to 7. 1, 2, 3, 4, 5, 6, 7. Okay, so basically what we're talking about here for the principal quantum number, there are 7 of them. Now we're also going to call that a shell. Next, we're going to have a sub-level to that. I'm going to call that a subshell. How many subshells depends upon which principal quantum number you're in. If you're in the first one, you have none. If you're in the second one, you have 2. If you're in the third one, you'll have, and so it gets getting more and more. Okay, as we build up that. Also, it's more and more because we're increasing the number of electrons. Shells, within the shell is a subshell. Within the subshell is an orbital. And within the orbital, you have a spin of the electron's direction, either up, meaning positive, or down, meaning negative. And that's going to be represented. Your book uses a square. Other books use a circle. Okay, so that's what it's going to look like.
And this spin is dictated because of the nucleus and the proton within the nucleus.
No,
It's bigger.
it's just inherent in the electron. It's either one or the other. It has nothing to do with anything else. It's just when we fill those orbitals, we're going to fill them first with spin going up or spin going down. It really doesn't matter. Because when we put another electron in there, it's got to be the opposite. Just like two magnets like each other, put them the same way, what do? So which do you think is more stable for those two electrons? Opposite or alike? Hmm? Yeah. So which do you think would be more stable? Think of two magnets. Yeah, or north and south with magnets. Okay. Batteries are plus and minus, but its concept is the same. So you want a magnet that's got its north pole to its south pole, just like when two magnets snap together. That's the most stable. If you try to put them north to north, south to south, they want to repel. So when the electrons are in the orbital, the most stable configuration for those electrons is going to be opposite spin or opposite magnetic poles. Okay, this was discovered by Team Gerlach and Stern. They shot silver atoms through a strong magnetic field. And the electrons split into two bunches, depending on its spin, whether spin is up or spin down. It went in two different directions. Okay, so we're going to talk in a little while about how those electrons are filled in the orbital. This is like charge, negative and positive charge. The charge is equal but opposite. Same with the spin. The spin is equal but opposite. Spin's either up or down, not halfway. This is why they call it the quantum mechanical model, because everything is one or the other. Right down the list. There's nothing that's kind of quasi in between. Now we're going to be using circles and squares to represent the actual places for electrons within the orbital. Now those places are going to depend on what subshell we're working in. Some of these have 7 places, some have 5 places, some have 3, some have 1. Depends on how high the principal level is. They're also named S, P, D, and F. And we'll get into those in a minute here. But it's represented, and usually by a arrow like that, rather than an arrow with 2 parts. And it really doesn't matter. Most people put an arrow like that in there. Okay, so whether this is a square or a circle, it's going to represent an orbital. Okay, you can only put 0, 1, or 2 electrons in that orbital. No exceptions. 0, 1, or 2. And if there are 2 in there, It's going to be opposite spin. Now, as we continue on, this will start falling into place. This is kind of real arbitrary, random kind of stuff here. Okay, and again, this is all for stability reasons. Which is more stable, which is more unstable? Okay, now this is a hard one. Hydrogen. Hydrogen, as you know, has one electron. So that means it's going to be in principal quantum 1. Principal 1 has only the S sublevel or subshell. And right here, it's missing a superscript 1. Which represents that one lone electron in the one orbital. Now you can figure out how many orbitals are in a subshell by counting on the periodic table. For example, here we've got 1, 2, 3, 4, 5, 6 possibilities in that one block of electrons. Okay, that represents 6 electrons. Each orbital can have 2 electrons max in the orbital, in the subshell. So how many orbitals do you think are in that block I just named? 6 electrons, 6 places. Each orbital can have max of 2. So how many orbitals would be in that block? 3. Why?
6 over 2.
How many 2s are in 6? 3. Now this is maximum. Some may be empty, some may be half full, some may be totally full. Okay, and this block of electrons happens to be called P block. So P block has 6 places, 6 possibilities of electrons. Each one is going to be divided up into 3 orbitals with 2 electrons maximum per orbital. And of course, they always give a name for all these rules. Pauli exclusion principle says you'd only have 2 electrons per orbital. And they have to have opposite spins. Now, this is for maximum stability. You may have orbitals that have spins the same, but it's not particularly stable. So the vast majority, like 99.9%, are going to be opposite spins. You may have a rare occasion the same spin. And then it wants to revert back to the opposite spin, which is a more stable configuration. Now these are the 4 sublevels or subshells. S, P, D, and F. Okay, sublevel or subshell here has only 1 orbital. That means you're going to either have 0, 1, or 2 electrons in there. P has got 3 orbitals, which you just talked about. So it can have 0, 1, 2, 3, 4, 5, 6. D is 5 orbitals. That means you're going to have 10 electrons max, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's F as 7, 14 electrons max. Okay, now these you absolutely have to know, and you absolutely will get tons of practice doing this stuff, using these levels. You won't have to memorize it. You'll just be doing so many problems that you'll just know it.
Can you go back?
Is this?
Yeah.
By the way, I'm officially going to all my lectures, I'm going to start having the notes I use to create them as well. I'll put those on modules. So when you look at the video, you can download those. You can make further notes on them. Okay. Okay. Now we talked about hydrogen already. So that's what hydrogen looks like. Helium has 2 electrons only. So we need to look at the electronic configuration for each one of those electrons. It's not the same. So each electron configuration is unique per electron. So if you have 10 electrons, you're going to have 10 configurations describing each electron. Its shell, its subshell, its spin, all that stuff per electron. So you have 4 values per electron. Okay, so helium has 2 electrons. If you go back up to the SPDF, S can only hold 2 electrons. So that means all it has is a S subshell. So let's look at the first electron in helium. That's what the first electron looks like. The second electron looks like that. So notice that the electronic configuration for each one of those electrons is unique. Also notice the orbital associated with that 1s shell is half full here, totally full here. Totally full is a big deal. Big deal. Because it cannot accept more electrons. That means it can't become an anion. Now, that's one of the reasons helium is so incredibly stable, because it's already in a stable configuration. Full subshell, full shell. Now, that's a big deal. And you're going to see all the noble gases have that consideration.
The subscript 1 and 2, could you explain why the second one is 2? For the second electron?
And this guy here?
Yeah.
1, 2.
Oh, okay.
It's the number of electrons in the subshell.
Okay, so how do we know that the first one only has 1 in it?
Because the way we do this is we have to start at the lowest level and look at how the electrons are organized. So the way these electrons are put into these orbitals, they do the most stable ones first. So the first one to go in, we have 1 more to go. The first one to go in is going to be this consideration. And then the next one, where are we going to put the next one? Well, there's room in here for another electron, so we're going to put it there. And we get to bigger electrons or bigger elements, you have a whole bunch of orbitals. I'm going to do uranium in a minute here. Uranium is about this long because it's got shell 1, shell 2, shell 3, shell 4, shell 5, shell 6, shell 7. Each one of those has lots of places to stick electrons. And what you do is I'm going to show you a technique one of my students invented 12 years ago in my class. I went through this. This is the mother of 3 kids. She was single and she had a job and she was in my class and she got an A in it. And I don't know when she slept, but anyway, somehow she did. Okay, so that's a good question. Just stick with me on this, okay? All right, so this is the configuration for helium. Now, sometimes the question will ask you, write the configuration for helium. And you usually just do the last one only. So for helium, the configuration is 1s2. And if they ask for an orbital diagram, you would then put in these guys. If they don't ask for the orbitals, you just leave that circle off. Okay. Okay. I'm going to talk about this in a second here, but we're going to jump back to this word degenerate. Now, it does not mean the same as a sex predator. Degenerate in the case of physics means the potential energy of the orbital are the same. So if one has one potential energy, if it's a degenerate orbital, it's got to be the same level. Otherwise, you cannot call it a degenerate orbital. Let's skip this for a while and come back to it. There's a guy named Dr. Coulomb a long time ago, ended up with this equation. You do not have to know this. This equation describes the potential energy between two charged particles. It has to do with their individual charges and how far apart they are. That's R. So the farther apart they are, there's less potential energy there, which means it's more stable. As they get closer and closer together, that potential energy increases, meaning it's less stable. Okay, I'm going to come back to this in a minute here. Okay, so let's look at this diagram here. This is a diagram of 1 through 5, not 1 through 7. And this continues on. Notice the trend here. Simple. Now, this is potential energy now. Remember, the lower the potential energy, the more stable. So of all the orbitals here, the 1s series is the most stable. Then the 2s and 2p. And notice that the s is more stable than the p. So elements that have only a 2s set of electrons are more stable than elements that have these p. Well, for example, we have lithium, and then it goes to boron. A boron are in the p area. Lithium's in the s area. But lithium has 3 electrons. Okay, so we want to have the most stable configuration for lithium. That will mean to put 2 of the electrons, because you only can put 2 per orbital, down here, stable area, and we have 1 left over. Where's the next most stable place to go? Here. So for lithium, we have 2 electrons, 1 electron. And it keeps going from the fills from the bottom up because that's the most stable, the lowest potential energy. Just follow along here. Okay. So what I just described is called the Aufbau principle. In other words, we fill the lowest potential energy levels first, all the way to the least stable. So F is going to be the least stable. If we're filling orbitals that have the same energy or degenerate, like P's, D's, and F's, those are going to be filled 1 per orbital. So you don't pair them up right away. You fill up, you put one in each orbital first before you pair it up. Because that spreads out the charge of that one electron in a symmetric way, which again, nature likes symmetry. I want you to remember this when we get into a lot of the bonding stuff in this class. If it's symmetrical, it's more stable than something that's unsymmetrical. Okay, so we have two principles so far. We have the Pauli exclusion principle, which says electrons have to be paired up inside an orbital. And the Aufbau principle says that we have to fill up if we have multiple orbitals per subshell, we have to fill them up one in each one first. Yeah.
So how do you know when you have multiple? So anytime you're with a P or a D, then you're doing the half fill first.
So let's do let's choose a carbon. And let's see how this spreads out in there. Okay. Carbon has 6 electrons. And we got to spread them out in all the orbitals available. This is what we have. So think of a post office where you can shove a letter in individual places or pockets. Okay, or in this case, we're using electrons into an orbital. 6 electrons. Okay, we want to put the electrons in the most stable orbital first. Which is the most stable orbital based on this chart? 1s. Okay, how many can go in there? 2. Remember, orbitals can only have 2. Okay, that leaves 4 left. Where are they going to go? What's the next most stable orbital? 2s. And since now we're down to how many electrons are left over? 2. Now, Aufbau says we can put 1 here and 1 there. We can't pair them up until the orbitals all have at least 1 electron in it. Okay, so that's what carbon looks like. That's how they're filled. Yeah.
Is there a rule, you can remember how the electrode was set up?
These are pretty straightforward till you get to this.
Right.
And the problem is the D's. D's and F's are, they don't fill according to this. There's a little, and there's a way to, I'll show you to remember that. Think of D's as dumb, F as failure. Okay, just keep that in mind now. Okay, so let's write the configuration now for carbon and all the electrons in it. Well, we're going to start off with the first shell, which is 1. It only has s electrons. And how many are in there? 2. What's the next one that fills? 2s. And how many are in there? 2. And what about the next one? And how many are in there? 2. So that's the electronic configuration for carbon. 1s2, 2s2, 2p2. Remember now the p's, we can put 6 in there. So if we looked at the outermost orbitals, okay, so we have this. So that the question asks you with an orbital diagram, this is what you'd put. If it just asked for electronic configuration for carbon, it would be this. Now, yeah.
So why do you go from 2s to 2p?
Because
Distance 2p is smaller than the distance of 3s.
yes, we're filling the most stable ones first.
Could you
explain the S, D, and P? Where's that coming from?
I mean, the S and the P.
Yeah, like, I know she has it on the PR table. Did I miss that part or something? That we're supposed to know that like that's the S part. That's
No, I'm going to show you a block how it's filled out, which is going to look like hers. Quantum mechanical people, the physicists, name these blocks, and it corresponds to either Greek or Latin. I forgot which one it is, describing what the orbitals look like in shape.
Okay.
And to me, it doesn't make any sense. S, I always think of sphere, but it doesn't stand for that because the S orbitals are spherical, but it doesn't stand for that. You know, and the P's are, they have lobes on them.
Mhm.
So that's one of those really esoteric questions.
Yeah.
Where do the SP names come from?
Well, I don't necessarily mean like why they were given those ones, but more of just like what are they?
Oh, okay. We're gonna end up with
Okay.
a deal like hers. All right, so you need lots of practice doing this. Now, they keep talking about ground state. Ground state, okay? Now, there are two states. Ground state and excited state. The ground state is all electrons are at their most stable orbital. So they'll always say, what's the ground state electron configuration for a Krypton? Now, Krypton has 36 electrons, so we have to account for all 36 electrons. So if we take this superscript, that should add up to be 36. So we have 2 plus 2 is 4, plus 6 is 10, 2 is 12, 18, 20, 36. So that's a double check. Make sure you account for all electrons. 37. So this keeps going out until we fill out all 37 electrons. So let's just do another one. Let's choose one up here. Let's do gold second. Gold is starting to get complicated. There's another reason gold is complicated because it's in the copper. We're going to have an exception of the copper group and the chromium group are exceptions. So we're not going to do those yet. Okay, let's do titanium. Okay, so how many electrons total does titanium have? 20 what? 22. Now we're going to use this chart over here to fill in 22 from the bottom up. So we've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so I started at the bottom just went up. So what does that look like?
It's next.
Huh?
3D is next.
Now, the problem here is notice as you go up, the D's are lower than the P's. So that means we have to fill the D's before the P's. And how many electrons do we have left? 2. So let's write out the configuration for titanium. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. All I did was I just repeated as this was going up. Okay, the trick here is the D's have to fill before the P's. Yeah.
I managed to recall a method to lay this out with, from scratch. Or do you know one? Or should I share that?
Yeah, let me show you one also. We'll
It might be
compare.
the same. You're probably the same.
Okay, so that's one way to write the electronic configuration for titanium. This is the method my students did. She said, start at hydrogen and take a walk through the periodic table till you get to your titanium. And as you go through the periodic table, write down all the stuff it comes through. Okay, so what shell are we at here at hydrogen? 1. We went to helium. How many electrons are in 1s2? Okay, so we write down on paper 1s2. Okay, we're not done yet. Now we go to the second shell. These are S's here. So 1s, 2 S's. Get over to the P's. So we're not at titanium yet. We have to write down all these numbers as we go. So we go all the way to the end here, and these are P's. And there are 6 of them because there are 6 places in the P's, and we're at shell level 2. So that's 2p6. Start here. 3s2 as we go. And we're still not at titanium yet. So we're going through all the 3 P's here, and there are 6 of them. You write down 3p6. We're here now. And this is level shell 4 or level 4. And there's 2 of them. Okay, so that'd be 4s2. And then we get to this inner area here. These transition metals are all 1 level below a principal quantum number you're on. So this is 4 here. So 1 less than 4 is 3. So these are going to be 3D. And how far into the D's do we go? 2. So it's going to be 3D2. So just let your pencil do the walking. And you write down the journey through the periodic table. Now, she had 3 kids. They're always telling them fairy tales. So she always comes with real simple ideas on how to do this. And she, in her study group, that was the method they used. And they all did really well. So is this similar to your method?
No. No. This is a way just to drop the energy level from scratch. And then just use that to fill it in.
Drop the energy level from scratch.
So you don't have to remember once you go to the S, once you go to the S is that, or once you go to 4, that D comes before P, and then you go to S.
Okay, another way she did it is when we're going across here, we're in the S's here. So these 2 are your S block. So they call them S block electrons. In the middle here are D block electrons. These are p block electrons. And these are f block down here. So as you're going through here, we're going from the s block, we hit a d block. Remember I said D is dumb? What's dumb down for? It's a 3. You're down 1. As you go across D, you get back into the P's over here. P's are normal. We get back up to the 4 level. So we're going 4, 3, 4. Now why we, from a physical perspective, the reason for that is the D's are a little more stable than the P, so they have to fill first for the most stable configuration. Now you can have all kinds of configurations, but some of them are super unstable, so they're not around very long. The ones that are most stable are filled like this. So on your periodic table, you have 4 areas you need to mark off. S's, D's, P as in Paul, and F's, okay? S, P, D, F. So when you're going through this, now you could either use this diagram to fill it in, or you could use that technique my student used. Yeah.
You were going, like, you were passing from that element. It'd be like that.
Okay, remember I said dumb and fail? The failures, instead of going down 1, they go down 2. So when you hit the F's down there, you're gonna go down 2 levels. So if you start on principle 6, you're gonna drop to 4F. And then in fact, you're gonna whip back over to the D's, which would be 5D, over to the 6Ps. Okay, so, all right. Now, in my opinion, this is very, very cryptic. Very cryptic. And, but the important thing, the reason why we're doing this, besides being a core concept in 1A, the reason why we're doing it, once in a minute here, we can actually predict the most stable ion, either gaining electrons or losing electrons that'll form, because the ionic, now these are neutral atoms we're doing here now. That means the number of protons equals the number of electrons. If the protons and electrons are not equal, then we have an ion of some type. Which electrons are lost? Well, we have 22 of them. Well, so titanium, what do you think that the 2 most likely candidates to be lost are?
E electrons.
The ones that have the most potential energy. If you get rid of those, your new configuration is more stable because the electrons are in lower energy level, lower potential energy level. So we're going to gain electrons. We want to gain them for stability reasons. We want to lose electrons. We're going to gain them for stability, or lose them for stability reasons. That's period. That's the only reason it happens. All right, so let's continue on this journey here. As you can see here, in this situation, the question would have asked, include an orbital diagram. So you need to include these guys here. And you can either draw circles or squares, whatever you like. So here's carbon again. We already did that one. Exactly like the way we filled it out. Okay, I'm going to do some practice here in a minute. There are 2 kinds of electrons in atoms: valence electrons and core electrons. Valence electrons are the electrons in the outermost orbital, the outermost shell. That includes S, P's, D's, and F electrons. The core electrons are the ones that have their all available orbitals are full. Okay, so look at carbon here. So which ones are core? Give me a color. Blue. So these are the core electrons. These. Now, when you talk about valence electrons, you talk about the highest shell number that automatically becomes valence electrons. The next one down and below are cores. So carbon has 2 core electrons because 1 less than 2 is 1, okay? How many valence electrons does beryllium have? 2. Okay, so this is the highest shell number. So those automatically become valence electrons. Anything less than 2 are core. How many electrons are in the core? 2. So 2 valence, 2 core. Now, sometimes you have a whole bunch of valence electrons. Sometimes you have very few. So let's look at aluminum. How many core electrons does aluminum have? How many core? How many yeah. Okay. So first of all, we're at 3 level shell here, right? What's 1 less than 3? 2. Okay, and below 2 is 1. So we need to count all the electrons in shell 1, shell 2, but not 3. So we have in shell 1, 2 electrons. What about shell 2? Huh? Now we have 2 plus 6 is 8. So we have 8 in shell 2, 2 in shell 1. So 8 plus 2 is 10. And notice 1, 2, 3 for aluminum. 3 valence, 10 core. Now, the reason why we're distinguishing between the two is because core electrons are horrendously stable. If you're horrendously stable, you don't do anything. If you're not horrendously stable, like valence electrons, they want to become more stable. So those are the ones that determine the chemistry of an atom, are valence electrons, not core electrons. Okay, beryllium, how many valence? Excuse me, not beryllium, boron. How many valence? 3. Okay, how many core? 2. So those 2 core electrons do not participate in any chemistry whatsoever. These 3 valence electrons do. Oxygen. Now we have a total of 8 electrons. How many are core? Yeah, 2. Means we have 6 valence electrons. Those 6 valence electrons are the ones that do all the bonding, whether ionic or covalent. Now we get down to these guys here because the D electrons come into play. Usually we don't talk a lot about valence electrons in the D and F shell. Traditionally, we talk about valence electrons in the first 3 shell levels or the first principal levels. Okay, so let's practice now. Let's do let's do iron right here. Write the electronic configuration for iron. Do all the little parts. There's a shorthand way of doing it in a minute, I'll show you. But you should be able to do the whole thing. Remember how to do this?
Kind of, sort of. I remember it more once I got this out.
Yeah, it's kind of weird. Where do you introduce that?
Mm.
That's, and then it kind of completes the picture, so it makes more sense.
This is from high school.
Yeah, you'll see that all over the place. The trick is, see, there are two periodic tables. There's this one,
Mhm.
which is, it's there. Some of them start here.
Mm.
So I always ask the department what periodic table we're going to use.
Uh-huh. Yeah, this one starts in every spot. 58.
Yeah, this is the one I usually use. This is from, right education. And the readings rounded to 2 decimal places. And
Yeah. Oh, this one's running for 3.
it varies.
Mhm.
Some departments like you to use, 8,
Yeah.
you
I
know,
like this one better because it's white, but I use the information on this one.
it's making sense. Mostly. All right, how are we doing? Now, your periodic table, you need to have that available. It is going to be your friend for this unit. Actually, for the course. Okay, so how are we doing, Tom? Let's whip this out. Okay, so iron. So if we do that little trick my student used, we're going to go through the whole periodic table. As you move along, you'll be writing down the blocks from which you're passing. So we're going to start on the first one, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we drop down 1 into the Ds. And how far over in the Ds are we going to go? 6 over. Now, if I ask you for an orbital diagram, all I want you to do are the valence electrons. These guys. You don't have to, because these are core electrons. Core electrons are super stable because all their orbitals and shells and subshells electrical are full. It's only the outer one. So an orbital diagram for this would be the S's and the D's. Okay, so how many are in the S? How many orbitals is that? The 4s. We're only doing valence now.
Oh,
So how many orbitals do we have in the S? How many orbitals are we going to have in 4s? 1. And how many electrons are in there? 2. Okay. How many orbitals do we have in the D section? 5. Because there are 10 spots, 2 per spot. That means it's 10 divided by 2 is 5. That means we have to have 5 circles. And how many electrons are going to fill those 5 circles? How far over is iron? 6, right? 1, 2, 3, 4, 5, 6. So we're going to put those 6 electrons in those 5 orbitals. So remember, we fill them one at a time. Then we start pairing them up. So that's what the orbital diagram for iron looks like. So this is subshell S, subshell D. So the subshells are S, P, D, and F. And that's for ground state, neutral, iron. You have to specify all those. Now, iron is a metal. Metals usually form cations. That means you have to lose electrons. Now, using this diagram here, we can predict the most stable configuration for losing electrons. For example, if we lost 1 electron right here, that subshell now is half full. Yeah.
Why would it not leave from an orbital that was already half full? Wouldn't it, because that has more potential energy?
If they're paired up, it's not as stable as by itself. So you want to lose the ones that are paired up first. Is that what your question was?
I thought they were more stable. Because they have opposite spins.
If you're gonna pair them up, that's the way you put it.
Yeah.
But it's more stable unpaired.
Okay.
So that's why you lose the paired one first.
Okay.
Okay, so there's a hierarchy in stability. This you need to know. The most stable configuration is a full shell. So we're talking about iron. The full shell would be the 4 S's are full, the 3 D's are full, and the full P's are full. So we need S, D, and P to be full before we have a full shell. Or we lose all those electrons, valence electrons, So we end up with core electrons. That's the only way we can achieve a full shell with iron. Okay. The next level of stability is a full subshell. So in the case of iron, this is a subshell here, the D subshell. How many electrons would we need to add to this to be a full subshell? 4. But as you know, iron is a metal, only forms cations. So we're not adding anything, we can only take away. So if we took away all 6 of these, we would have a full subshell of the S's. Now that's a lot of electrons to take off, which doesn't happen. The next level of stability is a half subshell. So now with iron, what could we do to achieve number 3? That we lose this guy here. That would allow us now to have a half subshell. So the Fe plus 1 is more stable than Fe 0 because we've achieved number 3 here. And then lastly, nothing to do with subshells or shells. That's where iron sits now. This is neither half full or full. So it's at the lowest stability level. So if we lose 1 electron, we go up a level in stability. So that's why iron frequently has a +1 ionic charge for this reason. If it loses 1 electron, its half shell will be, if it's a subshell will be half full. Half full is better than no combination. Okay, so how we got, let's practice this some more. Okay, so why don't you work on okay, why don't you work on those 3? Now I'm going to be giving you some worksheets tonight with lots of this practice. And you've got to do, unfortunately, a fair number of these, unless you've had this before and it's recent memory and you're comfortable doing this. But if you're not comfortable doing this, you need to practice a lot. And by the way, this is what determines the periodic trends on the periodic table, is what does the valence electronic configuration look like? And if you know how to do this already and you feel comfortable, I want you to predict the 3 ions that iron usually forms. And tell me which is the most common, least common. And you understand, obviously, why. I wonder if the Truckee campus is closed. There's a big fire right at Truckee. They're ordering evacuation. So if you got these done, look again at iron. Tell me the 3 ions that iron would probably be more stable in the way I've written it, at the neutral. This was not a good day for Erica to be gone. Okay, so let's look at iron again. Okay, so who can tell me one way to make iron, ground state neutral iron, more stable based on these rules? Yeah,
Take away an electron.
get rid of 1 electron, okay? That makes that Fe+1 because we've lost an electron. What's the configuration for Fe+1? Let's look at the orbitals. How many electrons does Fe+1 have valence-wise? Okay, well, there are 2 in the S, right? And 6 here. We lose 1, we have, well, 2 and 6 is 8. Losing 1, that'd make it 7. So we fill the S first. 3, 4, 5, 6, 7. So that would be orbital configuration for Fe+. We write that as 4s2, 3d5. Now, why is that more stable? Yeah, we've reduced it down, so we have a half full shell. I mean, half subshell. Okay, that's good. What about another one? There are 2 more possibilities. So you start with the neutral one and take away, yeah.
Take away the remaining 5.
So we're talking about it +6 then, right?
Yeah.
And that's a lot of electrons. So basically, we take away all of those. That would be 4s2. And you can write 3d0 if you want, or you can just leave it off. I like to write it because with those do exist. It's just that there are no electrons in it. Okay. That's a very rare ion, by the way. Okay. So far, the Fe+1 is the most stable between the two. What else? Yeah. -1.
Where you basically just fill in all the shells.
So that'd be -4 then.
Yeah, so that,
Oh, I thought you said -1.
no, I said that.
And cations, metals usually don't form anions. They usually form cations. However, that's what that would look like. Technically more stable because we've gone from a half subshell to a full subshell. Okay, what are their two cations? What iron? Hmm?
Fe+8.
Lower numbers. When you start losing lots and lots of electrons, they don't happen as frequently as one if you lose like 1, 2, or 3 or something like that. What else? You guys are on the right track. You're thinking logically. More than half? I mean, lose 3? Okay. Well, you wouldn't gain 3 because you wouldn't fill it up. You have to gain 4. But you said, or you can lose 3, right? Is that what you said? Okay. Now, if you lost 3, what you'd end up with is you lose the S's and you lose one of the D's. Okay, and that happens to be one of the common ions for iron. Yeah.
How come you lose S's if they are filled before D's?
Experimentally, that's what happens.
Because they're all valence electrons technically, so it doesn't matter.
Oh yeah, we're only talking about valence electrons.
Yeah, but I'm saying you can lose S's even though they're before D's because they're all considered valence electrons. So that at that point, they're just all equal transport.
But see, with the S's, you only need to lose 2.
Yeah.
For to do that with the D's, you have to lose 5 or 10. Or, so it's easier for the atom to lose 2 than more than that.
Okay.
So in fact, continuing on your point here, all the D's always form a +2 cation
Okay.
and get you what electrons they lose. The S's, yeah. And then why? There's two in the S.
Okay.
So it's always a +2, yeah.
So the reason why Fe3 is because it's stable, because all that function is stable. There's
The half filled subshell, exactly. So we're losing stuff to achieve one of those 4 options there, or one of the 3 top options. The 4th one is nothing. Okay, so we want to go to a full shell, full half shell, a half subshell. Those 3 options we want to lose or gain electrons for. Okay, what else? And you mentioned losing the S's. So that would be an Fe plus 2. So that would look like this. Okay, so between Fe plus 2 and Fe plus 3, which do you think is more stable? Plus 3, I agree. Because this has got some baggage here, because this is not half full. We're here, we lose this one and these two, so we end up with half full. That's why ions form, because the resulting configuration is more stable. And you can go down, and I was talking to her about a lot of the cations form plus 2s, and they lose these S electrons. It's easy for an ion to lose 2 electrons than it is to lose more. So a lot of the D elements in the middle there form a plus 2. That doesn't mean it's the most stable, but they will usually form it. Okay, all right, that's what we've done for today. I'll post some worksheets on this. I've got a lot of worksheets where you can practice this. You need to practice both doing a neutral atom and a ion.